So good day, everybody. I am Stefan van Veen, sales manager for OD Security. We are the manufacturer of the Sotar RS X-ray body scanner. I will be giving this talk together with Joost Deutekom, our marketing manager. Our presentation of today will be about AI contraband detection in our product, the Sotar RS body scanner, which is used in prisons, airports, and border crossings. So what we know is that contraband is a universal issue. We see all kinds of contraband at prisons, border crossings, and at airports. So we also know that this is happening everywhere around the world, although in some countries more than others. So what we see is all different kinds of illegal items that people try to smuggle in. So for example, over here, we see a knife, razor blades, bullets, but also larger amounts of drugs and smaller amounts of drugs as well. And besides that, we see smaller phones, USB drives, tobacco, marijuana, and also SIM cards. So if we look at these categories, what we mainly see in our prison is drugs. Besides, we find weapons and phones and electronics as well. So how does it enter the facility? So there's many different ways contraband can be smuggled into facilities. For example, through parcels, but it's also possible that items come in through drones. But the vast majority is coming in through people, actually. Like 60 or 80% of all the things that are smuggled in is going through people. So we have different kinds of technologies that we use to find these kind of items on the body. So for example, we have a metal detector, which can find metal. We also have, this is like a method, like a strip search method, that you can find metal very easily, of course, phones as well. But drugs is mostly carried at the private parts of the body, so it's more difficult to find these with a strip search. So we have millimeter wave body scanners, which we see at the airports, for example. You can find weapons, you can find mobile phones, and you can also find drugs, but the limit is that you cannot find it inside the body. Then we have the X-ray body scanner that we manufacture. In this case, you can find weapons, even if it's a non-metallic weapon, like a ceramic knife, for example. We can find phones, like even the smaller kinds of phones that you see that I just showed you on the previous slide. We can find drugs. And the big benefit of having an X-ray body scanner is that you can find all these items on the body, inside clothing, or inside or on the. So there's no limit of detection looking at where you can find these items on the body. So what you need for that is the Sotar RS body scanner. And this body scanner can make scans, like X-ray scans, that you can see in this slide. So for example, on the left side, we see a male carrying several drug balloons inside his intestines and inside his stomach. On the right side, we see a female carrying 3 bullets in her armpit. And she is also carrying a knife, which is wrapped in her body cavity. And just above that, there's a very small tube, which can carry 1 bullet, which is also carried in the body cavity. So using this technology also means you're very dependent on the operator. We focus on making the system very user-friendly to assist the operator. The operator can still miss contraband, especially when the item is smaller, for example, when there is a lot of pressure on the operator. So to make it more easy for them, we do an in-depth training. We make the system very user-friendly, as I said. But we also want to further assist the operator. And that's why we introduced the TIA, which is an AI-based operator digital assistant. So I'll give the word to Joost, which will explain the process of the AI.
Thank you very much, Stefan, for introducing the product. So I think this gives you a little bit of background what a body scanner is and how it functions, and that's key to now understand how AI can further help to improve finding contraband. So for that, I will take you through our development strategy, and it goes from data gathering to processing, backbone training, fitting, and constant new technologies that will come. Starting point, obviously, being data gathering. So you need lots and lots of data when you start to work with AI in any fields, basically. And we work with AI in the application of vision, so vision technology, computer learning. We have got many sites around the world that work with our instruments, and we collaborate with those sites, so with our direct customers, to collect data. And we get, on a daily basis, we get scanner results that we basically harvest and put into a data set, and that we further process. So this is thousands and thousands of scan images. Now, the data set then needs to be split into certain categories to be able to work with it. And we make a rough classification based on images that are what we call truly negative. So like the image you see over here, this is a person being scanned that has no signs of contraband or other objects within the human body. Then there is positive scans, like for instance, the person here who has a medical implant. So within that medical implant, that's something that isn't part of the human body. So we classify that as a positive image. The same could be if we find contraband, or if we find or the types of contraband that Stefan just explained. And then there is examples where the person is just wrong positions. And here you already see some of the dependence that you have as an operator. If you're starting to make the scan, it is important that the person is positioned correctly on the platform and not having, for instance, the legs crossed, as you see here in the image. Now, within these images, if we put it in these kind of buckets and classify them as such, we are using the negative images for training and the positive images for testing and validation. And the reason we do this is we work with what we call sort of anomaly detection. So we train the algorithms, the AI algorithms, in what does a normal human body look like? So what does a human body look like without any contraband in there? And by training it in that way, in the end, we'll be able to find all the abnormalities. So the algorithms will learn, and this is the self-learning element of AI. They will start to recognize patterns, and they will start to learn, right, this is an object that isn't supposed to be in the human body because it doesn't fit within the data set that I have been trained on. And now this is an anomaly from that. So that's the data processing. And the first thing, if you start to work with a neural network, so the actual AI models or algorithms, if you like, is that you need to train these networks in being able to work with X-ray images. So we feed the backbone with X-ray images, and we don't feed it with a complete X-ray image because those images are too large to process. So we give it a portion of an X-ray image, and what it will do, it will do feature extraction. So it will start to learn like the kind of grayscales, the way the images are built, what it sees on those images, and it will start to get familiar with X-ray images. Because you need to remember, these neural networks are used for many different purposes, so we always need to train it for the purpose we are going to use it. The next step in our development strategy was an important decision, the split or the decision between moving to supervised versus unsupervised learning. And what I would like to do is take you through those two options and the differences that they make. So I try to simplify by giving an example with using fruits. And I will use that example throughout the presentation. If you have a series of fruit and you would process those through a algorithms, through a neural network or an AI network, then if you do a supervised learning, what you could do is tell the network, right, this is, if you see this object, that's an apple. So you train it and you tell it specifically, you need to find a lot of images with apples, and every time you have an apple in that image, you show, all right, in this portion or this part of the image, there's an apple. And that's how you train the network. Now, what it will be able to do within that data set, it will find all the apples for you, and it can tell you this is an apple. If you have unsupervised learning, it will be looking into patterns in a more generic way. So it will be able to split different groups based on the images or based on the data it has. And it will be able to group the strawberries, the bananas, and the apples. But it will not have any idea what it is it is grouping. It's just recognizing similar patterns and putting those together. Now, what does that mean from a development standpoint where we are in the application where we are, so with X-ray images for prisons? So if we have supervised learning, we would train the algorithm saying, all right, this is, for instance, a belt, this is a watch, and every time something similar passes by, the algorithm would say, all right, I found a belt, I found a watch. And the same would be true with contrabands like knives, etc. The other direction, the unsupervised learning, and this is the path we have chosen because we feel this is the giving us more flexibility, and I will explain you why, is we feed the algorithms with, well, what I said earlier, negative images. So images of persons that have no contraband or no items within or on their body. This is an example of one of those images. And we feed it with hundreds and thousands of images like that. So the algorithm will start to learn, all right, this is what a human body looks like. This is what a human body looks like. This is a body without any contraband. So it starts to build a pattern in that way. Now, if we now use it in a real life situation and we run it, and you feed it with an image where there is something standing out. For instance, the previous image I used with the belt and the watch, it will be able to find those items. So it will see, hey, this belt I haven't seen, that's not part of my normal data set. It's not part of a normal body. So I find that, and the same with the watch. So you will find those objects, but it will not be able to classify it as a watch or as a belt. It will just highlight it. And this gives much more flexibility because independent on where contraband will be or the type of contraband you're looking for, we will find it, or the algorithm will find it because it knows what a human body is supposed to look like, and everything that stands out from it will be highlighted. So that's an important decision. Then if we move to fitting, now the backbone is trained, so it knows how to read X-ray images, and now we process all these negative images through it. And it starts to learn certain patterns in that data set. And you do that by what I call a Gaussian mixture model. And I want to explain that also briefly on using the fruits again. So if you would plot the fruits it would find, then you will see that there will be certain clusters of information that's very similar, like the apples, like the bananas. Now, if you find the center of that data, you can make a normal deviation or a standard deviation from that and process multiple algorithms on each of those clusters. And your results will be much better. And that looks a bit like this. So the normal bell curve. And that's how you improve the algorithm in being able to better detect items that you want to find. Now, finally, the final step within in our development strategy, there's constant new technologies coming available, being invented. So we are always on the outlook for new things, and those will feed into our data set, and we will start to reuse it. The nice thing is that if you have that data set, it will only grow, but you can continue to use the data that you already have. One of the things we're looking now at is a new method of tiling these images, because one X-ray image is by itself too large for algorithms to process, so that would take too much time. So you break it down into smaller chunks, and if you have those items, you can basically process it chunk by chunk. And we're looking in smarter ways to do that. So that's a next step for us. So now looking at the results, what does that look like? So we've got a normal X-ray image coming out of our instrument that if we would process it with AI, it produces in the backend a heat map. That's what you see here. So again, this heat map is showing the anomalies. It's showing those items that stand out from the normal data set. And you see in the light blue and yellow and even red colors where there are items that are not supposed to be there or are different. And then what the operator eventually will see is nice bounding boxes around these. And this is an example where a person has surgical implants, so metal knees, and those will be clearly highlighted. Another version of the results. So I want to give a quick demo of the software, how you would use it in real operation. So you log into the software. The first thing you need to do is make a scan or select a previous scan. Is what we do right now. So we take a previously made scan. You have the image of a person, and then if we process the AI, so we ask or we ask TIA to analyze the image, it finds 3 objects. So over here, you can adjust the color to make it easier. But here you already see how dependent as a user you are to make the right selections. Behind the ear, there's some drug. I believe it was cocaine. This person also holds something in their hands. That's not contraband necessarily, but it's standing out from the normal images. So therefore it finds it. And then within the feet, there's some screws in the ankle, so a medical implant. Those are metal objects. If you move it to the emboss settings, which we are on right now, you see that the metal, more dense objects pop up very clearly. So you can play with the light settings to make it more visible. So finally, the impact of this in prison settings and but also at customs or other border crossings is you reduce the risk of human errors. You have a digital assistant that will be on your shoulder and helping you to make sure nothing is missed. And that's an important item, and to make sure you don't miss these items, because it will help to increase the overall safety in a facility or in the setting you are in, both for visitors, staff, and even inmates. So thank you for your time, and hope this was a clear explanation.
Thank you so much for your presentation. It was a really engaging one on prison contraband, and for taking the time to talk with me now. I just wanted to ask you a couple further questions about your presentation, if that's okay.
Yeah, sure. Yeah.
Perfect. So we're hearing about this integration of AI in all technologies across the industry, which of course is beneficial, but are there any cons to this?
I think the main con, or the one that you should really consider, is we are becoming to some level dependent on it, but you want to make sure that your operator, and I'm speaking for our application, that the operator still makes the final judgment, so that a person should still fully understand the work he or she is doing and not completely rely on the AI algorithm. So continue to think for yourself, and also, if needed, disagree with what the algorithm finds, or even sometimes learn from something the algorithm finds which you didn't detect. So there's always a level of making sure you don't, you keep thinking and you keep on your own toes.
Yeah, so I think most important on that one is also accuracy. So if we look at different AIs in the market, you see there's a lot of false positives as well. So that's something that we try to focus on as well. So make it a very accurate AI model that can be used very effective by the operator. So in that case, you also have less false positives as well, which also is more user friendly for the operator as well, because they don't have to all the time deny these false positive flags on the scan. So.
And you spoke about the breaking down of data sets. Why is this a necessary step? And does this have to happen with all AI algorithms?
I cannot speak for all AI algorithms, but within the field we are operating, especially using, from an AI perspective, using vision technology, it is a key step, because you need to build a data set. And as I explained, the way we do anomaly detection by training the algorithm what the human body looks like, we need to make sure those are actually good and clean images. There's no contraband in there. If you take the other approach, the supervised learning approach, you would still need to classify images and highlight where there's contraband, and then putting boxes around it and learning it. All right, this is what a knife looks like, and this is what a drug balloon looks like. So there's always important that you get quality data in. Rubbish in is rubbish out.
And I suppose feeding that algorithm with those neutral images without contraband is I suppose the only way to make sure that you're protecting against any objects that are completely new to the algorithm.
Exactly.
So that's also why we chose that strategy. So if there's any new kind of drug in the market that is being carried in the body cavity or carried somewhere else on the body, we're able to find that. So that's also, looking at the future, a very important thing.
Sorry, Stefan. Oh, sorry.
Well, we've seen over the years in working in this field, we've seen many creative ways in how they where and how they hide contraband. For instance, in the mouth, they carve a small pocket into their mouth tissue, or they put something over their teeth where they hide small amounts of drugs, or like a SD card and things like that. So there's definitely a lot of creativity in getting drugs in. So we felt, as we were going down the path of AI development, we needed a solution that's flexible and robust against that kind of creativity.
Yeah,
that's exactly what I was going to say. Is you never know what kind of next evolution these kind of people might be thinking. No. Anyway, so you also spoke about solution and training. Is this something that needs to be changed dependent on the end user? So, for example, is a prison scanner different from an airport scanner?
On training based, if you look at the prisons, so there's no extra training that is needed for the operator, only that they need to be aware that they have this feature TIA, as we call it, that will point out where to look at at the body. So it's actually helping them more. So I would say not necessarily more training needed. If you look at the difference between prisons and airports, the scanners that we sell to airports, they're mainly interested in the abdomen area for finding drug balloons inside the body. So the training is also a little bit different if you compare those. So the focus for airports is more on the abdomen area, and with prisons, contraband can be everywhere. We see them inside shoes, in the mouth, as Joost said. So the training is a little bit different in that case.
And just to add to that, I think the most common scanners that you see at the airport are the millimeter wave scanners. If you compare, for instance, how we train operators versus an operator for a millimeter wave scanner, those are more trained on how to operate them, because the software will just show, all right, I see something suspicious in this area. Where with the X-ray, you're actually looking like a real X-ray image of a person. So a lot of our training is not so much around how to operate the machine, but much more what a X-ray image of a human body look like. And Stefan, you've done a lot of training. You train on, like, you've got 2 lungs, so you can compare those. You've got 2 kidneys, which you can compare. So there's a lot of similarities left and right. And finding those and scanning the body from top to down.
Yeah.
And as the scanner does use X-ray technology, should end users be concerned about any radiation exposure?
The system uses a very low dose of X-ray, which can be compared with flying 20 minutes at 30,000 feet in an airplane, which equals about 2 microsievert in that scenario. So if you fly on 30,000 feet for 20 minutes, it equals an average scan on our scanner. So a lot of people are not aware of that, but when they go flying out to whatever kind of country, they're being exposed to cosmic radiation. They're also exposed to, actually eating bananas is also exposing you. A lot of people don't know that as well, which is eating 2 bananas equals 0.5 microsieverts, which is a level 1 scan, a lower dose scan on our system. So that gives a little bit of a comparison of how normal life exposure compared to our system. So it's a very low dose. And besides that, there's also, we have a database. So every person, like for example in a prison, will be recorded, and the cumulative dose of that person will be recorded as well. So at the moment that the maximum dose is received, the maximum allowed dose per year or per month or per week or per day, the system will give a notification to the operator that it cannot make any scan.
Okay.
And for the operator, there's no
exposure for the operator, so that's important as well. So yeah.
Okay. Fantastic. Well, thank you for taking the time to talk with me and for doing your presentation here at Security Bio Live. If anybody has any further questions, please reach out to Stefan or Joost on the platform itself, and you can find out more from them. Thank you.
Thank you for having us.
Thank you for your time.